Today's lesson goes into detail on the quantum mechanical model of the atom. We recall that the Bohr model of the atom developed the concept of energy levels. And we also are aware that Bohr's model was good, but failed to explain the energies absorbed and emitted by atoms with more than one electron, or if we saw multiple lines of the same color within an electron spectra. Bohr and Rutherford focused on an atomic model where the path of electrons surrounded the nucleus like a little particle. However, Erwin Schrödinger came along and said that the electron actually behaved as a wave. And as a result, he used a lot of calculus and mathematics to develop the quantum mechanical model. There were three major scientists who began to notice some interesting things about the electrons in energy levels. Schrödinger came up with the idea that there was a probability of finding electrons in a given location. Heisenberg said that it was impossible to know the exact position and the exact speed of an electron at the same time. And then de Broglie claimed that electrons had wave-like properties and that they moved in wave patterns. So the idea that the electrons were behaving as waves was a rather revolutionary idea and paved the way for this new model of the atom. So treating electrons as wave-like particles allows us to apply this to this quantum model where allowed energies are given to an electron, and also it states how likely it is to find the electron at certain locations around the nucleus. If you consider the propeller blades of these airplanes, the idea that you know that the propeller blades, that there's usually three of them, and that they're flying around, it's kind of that idea. It's a blurry region. You know the probability of finding those propeller blades, but at any given time, they are moving around, and you cannot tell its exact location. So now when we look at the atom, we usually denote it with like a bit of a cloud region. So a fuzzy area here where the electron is likely to be found. The cloud is more dense where the probability of finding an electron is high. And this is usually somewhere around the nucleus. So you can see that right here, this is a little bit lighter color going all the way around, as opposed to, again, a deeper color here, indicating that this is the region where you would most likely find an electron. So within an energy level, an atomic orbital is the region of space in which there is a high probability of finding an electron. And it looks a little bit different. So again, it's these density maps here where, again, it's, more dense right here, closer to the nucleus, and less dense the further you get away from it. So an orbital is thought to be an electron cloud. And the definition of an orbital is this region of space where there is a probability of finding an electron. And it's actually a 90% probability. So to find the electron at these given locations, these were derived from these wave equations. So the Schrödinger equation we saw a little while ago, and some mathematical calculus in order to determine actual shapes of these orbitals where you can find the electron. So we've already covered the fact that as we move through the different energy levels, the number of orbitals corresponds to the type of energy level. So in the first energy level, we only have one orbital, which we call an s orbital. In the second energy level, we have two orbitals, or sometimes we call them subshells, which are called S and P. In the third energy level, we have three orbitals or three subshells, which get repeated. So SP, and then a new one, which is the d orbital. And in the fourth energy level, we have four subshells or four orbitals, and SP and D are all repeated, plus this fourth orbital. Beyond that, we don't have a fifth orbital. And the reason for that is that no element on the periodic table currently has enough electrons to sit in a fifth orbital. here's just another way of showing all the orbitals that exist for each energy level. So one of the confusing things with quantum mechanical model is some of the terms that we use. So even though we call these an orbital, they're also called subshells, okay, meaning that they sit within the shell of an energy level. And so the different orbitals that we have, those letters, correspond to the names of the subshells. So the s orbital is given the name or the letter S because it looks like a sphere. The p orbital is actually a peanut-shaped orbital. So you'll see it right here, and it's got like two lobes. So we kind of draw it sometimes like this, sort of like a figure eight, where there's a lobe above, a lobe below. It kind of looks like a peanut shape. The d orbital right over here is like a double peanut. So again, here is sort of your one lobe, right? Or your two lobes of one peanut. And then right here is the other two lobes of a second peanut. And then the f orbital is given that name for the term flower. And so you can see that there's many orbital lobes, and that gives it a little bit of a flower-like pattern. Now, within each of these orbitals, there are different locations where these electrons can sit. So the s orbital has only one shape or only one location. And the p orbital has three different orbitals or three different locations. The d orbital has 5 different locations where electrons can sit. And in the f orbital, there are 7 different locations. And this is why you can place a lot of electrons into each of these energy levels. This is a nice image of showing the overlap of first and second energy level and the overlap of s and p orbitals. And you can see the different shapes. You could see the spherical S shape in the middle. And then you can see the lobes of those peanut-shaped orbitals. And again, they all overlap, and together they make up a sphere-like shape. Now, a very important thing to be aware of is how many electrons can we place in these first 4 energy levels. And this is the most important part right here. You have to know that you can only stick a maximum of 2 electrons per orbital. So in the s level, you only have, or in the s orbital, you only have 1 orbital location. So you have a maximum of 2 electrons. Remember that in the p orbital or the p sublevel, you can have 3 different locations, also called 3 orbitals, times 2 electrons per orbital, so a maximum of 6 electrons. In the d orbital or d sublevel, you can have 5 different orbitals. And when you can place 2 electrons in each of those orbitals, you get a max of 10 electrons. The f sublevel has 7 different locations. Times 2, you can put in a maximum of 14 electrons. Now, we take all of this information, okay, electrons behaving like waves, the fact that there's these orbitals, the fact that there are multiple orbitals in p orbital or d orbital, the fact that you can put 2 electrons in each of these locations. And we take all of this and then we put that together to draw electron configurations, which is like drawing the new way of representing Bohr-Rutherford diagrams, but it's going to look totally different. And we use a couple of principles. So we use something called the off-bow principle, and this is where we make sure that the electrons occupy orbitals of lowest energy first. This is similar to a Bohr-Rutherford diagram. There's also a principle called Pauli exclusion principle, where it says that an atomic orbital may describe at most 2 electrons. Okay, so you can only put 2 electrons in these little orbitals, and that they must have opposite spins. So we know that electrons do spin around, and we indicate that when we draw these little diagrams. And then we have Hund's rule. And Hund's rule says that electrons that occupy orbitals of the same energy have to in a way that makes the number of electrons with the same spin direction as large as possible. So what we do is we place these electrons as singles with a certain certain spin. They all have the same spin. And then we come back and we pair them up with opposite spins. We also have to be mindful of orbital overlap. So when we get further away from the nucleus of the atom, so starting over here in energy level 3 and 4, the orbitals start to overlap because the space around these energy levels is not as great. And so we have to be mindful of orbital overlap when we draw these diagrams as well. There are different ways to know how to overlap the orbitals. You can use a schematic such as this right here. It's not a bad schematic. I tend to not use it. But what you do is you line up your orbitals in sort of order of the energy level. And then you know that there's, orbitals, the number of orbitals corresponds to the energy level that you're dealing with. And then you fill them on this diagonal. Okay, so you'd fill 1s first, 2s next, 2p, 3s next, 3p, 4s after that, 3d, 4p, 5s in that order, and so on. And this allows us to, especially over here, right, deal with the overlap. I prefer instead to deal with the periodic table. So right over here. And the periodic table is designed and set up according to energy level and orbitals. So what we'll notice over here is that everybody in this group right here, any element that we are looking at and we want to draw a diagram for it, its last electron is in the s block. Okay, so you'll notice that all of them correspond to the s orbital. Over here, any element that we deal with, their last electron will be sitting in a p orbital. Transition metals over here, their last electron in that particular element will be sitting in d orbitals. And then the only two f orbitals are our actinides and lanthanides, and they correspond to these f orbitals where you can place up to 14 electrons. So there's two ways to represent electron configurations. You can either write them out, okay, and when you're writing them out, we take on a notation like this, where we have the energy level here, given by the larger number. We have the orbital type, okay, or the sublevel, and then we'll have a little superscript of a number, and this is the number of electrons that's actually sitting in each of your orbitals. If we want to draw them out, it's going to look something like this. And this is where we show the spins of our electrons. We show the different locations that we have within these orbitals. So remember that, P has 3 locations, D has 5. And we're using things like Hund's rule, where we're putting all, spin ups first, and then we come back down and we pair them up. When we get a bit more comfortable with electron configurations, oftentimes chemists will write condensed electron configurations. And this is where we abbreviate the electron configuration, because they can get kind of long, by using the preceding noble gas. And then once we pick the noble gas just prior to your element, we just simply state any energy levels and orbitals and the number of electrons that we need to get to the particular element that we are interested in. So now we'll move into another lesson where we will actually practice drawing and writing out these electron configurations.